Hello, friend. Welcome back. Or if this is your first time here, welcome to a place where the night slows down, where questions don't need hurried answers, and where science becomes something softer. Tonight, we're going to look up, not with urgency, but with wonder, because somewhere in the darkness above us, there's a galaxy, a neighbor, a trillion points of light traveling through time to meet your eyes. And tonight, we're going to ask a question that sounds simple, but opens into infinity. How many stars are there in the Andromeda? Some nights when the sky is clear and the moon stays low, you might see it, a faint smudge of light, soft like breath on glass. Ancient cultures saw it too. They called it a cloud, a mist, a whisper in the heavens. For thousands of years, no one knew what it was. Just something out there, something waiting. Before we begin this gentle drift through time and starlight, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. These small gestures help this space grow, help more people discover that learning doesn't have to be loud. It can be a lullaby. Now, let's drift. Tonight, we're asking how many stars live in that distant light. The answer isn't just a number. It's a story about how we learn to see, how we learn to count the uncountable, and how even now, with all our telescopes and equations, the universe still holds its mysteries gently just out of reach. You don't need to understand everything. Just rest and let curiosity do the listening. The Andromeda Galaxy, M31, as astronomers call it, our closest large galactic neighbor. It sits about 2.5 million light-years away. That means the light you see tonight, if you're lucky enough to catch it, left Andromeda when our ancestors were just learning to walk upright. When the world was colder, stranger, younger. The photons that touch your eyes tonight have been traveling since before we were human. Think about that for a moment. The light is old, older than language, older than fire, older than the first story ever told under stars. But here's what makes Andromeda even more remarkable. It's not just far, it's vast. Researchers estimate it contains around 1 trillion stars. 1 trillion. That's a 1 with 12 zeros. 1 billion. If you tried to count one star every second without sleep, without pause, it would take you more than 31,000 years to finish. And that's just Andromeda. One galaxy among hundreds of billions. Scientists suggest that Andromeda is actually larger than our own Milky Way. Where our galaxy holds somewhere between 200 and 400 billion stars, Andromeda seems to cradle more than double that amount. It's a giant even by cosmic standards, a spiral of light rotating slowly through the void, patient and endless. But how do we know this? How can we possibly count stars we can barely see? To understand the answer, we need to go back. Back to when Andromeda wasn't a galaxy at all. When it was just a mystery in the night sky, a pale blur that refused to be explained. The first recorded observation comes from the Persian astronomer Abd al-Rahman al-Sufi in the year 964 CE. In his Book of Fixed Stars, he described it as a little cloud. He saw it with nothing but his eyes, the way you might see it tonight if you go somewhere dark enough. No telescope, no camera, just human vision and patience. Al-Sufi didn't know what he was looking at. He couldn't have known, but he recorded it. He honored it with attention. For centuries after Andromeda remained a puzzle, European astronomers called it a nebula, a Latin word meaning mist or cloud. They assumed it was part of our own galaxy, a patch of glowing gas somewhere in the Milky Way. Some thought it might be a birthplace of stars. Others believed it was a dying remnant, the ghost of something ancient. Even when telescopes arrived, the mystery deepened. In 1764, the French astronomer Charles Messier catalogued it as the 31st object in his famous list, Messier 31, or M31. He was hunting for comets, and these smudges of light kept confusing him. So he made a list of things that weren't comets, things that stayed in one place, soft and still. Andromeda made the list. a beautiful distraction. But no one yet understood what it truly was. Here's a question people often get wrong. They assume that once we had telescopes, once we could magnify the heavens, everything became clear. But that's not how discovery works. For more than a century after the telescope's invention, astronomers looked at Andromeda and still couldn't agree. Was it inside our galaxy or beyond it? Was it nearby or impossibly distant? The tools improved, but the questions remained. It's humbling, isn't it? To realize that even with technology, even with brilliance, the universe doesn't give up its secrets easily. It asks us to be patient, to look closer, to doubt what we think we know. In the early 1900s, the debate reached a peak. Some astronomers believed the entire universe was just the Milky Way. Everything we saw, every star, every nebula, all contained within one galactic boundary. Others whispered a more radical idea. What if those spiral nebulae, those faint clouds, were galaxies themselves? Whole islands of stars separated from us by unimaginable distances. The argument became so heated that in 1922, astronomers Harlow Shapley and Heber Curtis held a formal debate at the Smithsonian. It became known as the Great Debate. Shapley argued that the spiral nebulae were part of the Milky Way. Curtis insisted they were separate galaxies far beyond our own. Both men were brilliant, both men were confident, and neither could prove his case. Not yet. The universe waited silent and patient for someone to find the evidence. That someone was Edwin Hubble. In 1923, using the most powerful telescope of his time, the Hooker telescope atop Mount Wilson in California, Hubble turned his attention to Andromeda. He photographed it night after night, searching for something specific. Variable stars called Cepheids. Cepheid variables are special. They pulse. They brighten and dim in a regular rhythm. And here's the key. The speed of that rhythm tells you how luminous the star truly is. If you know how bright it really is, and you measure how bright it appears from Earth, you can calculate distance. It's like seeing a candle far away. If you know it's a candle and not a bonfire, you can estimate how far it must be for it to look that dim. Hubble found Cepheids in Andromeda. He measured their periods. He did the math. And the answer was staggering. Andromeda was nearly 1,000,000 light-years away, far, far beyond the edge of the Milky Way. It wasn't a nebula, it was a galaxy, a separate universe of stars. Later measurements refined the distance. We now know it's about 2.5 million light-years away. But Hubble's discovery changed everything. Suddenly, the universe wasn't one galaxy. It was vast beyond comprehension, full of galaxies, full of possibility, full of light. And that soft smudge in the sky, that little cloud Al-Sufi saw more than 1,000 years ago, it became a neighbor, distant, yes, but real. A place made of stars, 1,000,000,000,000 of them. Scientists suggest that when we look at Andromeda, we're looking at our own future. In about 4.5 billion years, the Andromeda Galaxy and the Milky Way will collide, not violently. Galaxies don't crash like cars. They pass through each other slowly, gracefully, their stars so far apart that almost none will touch. But gravity will pull them together. They'll merge, become one. A new galaxy larger than either alone. Astronomers have already given it a name, Milkomeda. By then, our sun will be older, cooler, possibly nearing the end of its life. Earth may not even exist as we know it, but the stars, those trillion points of light from Andromeda, will mingle with ours. They'll dance together in the dark, creating something entirely new. It's strange, isn't it? To think that something so far away is also coming closer. That distance isn't always permanent, that even galaxies in their slow cosmic way are reaching for each other. For now, though, Andromeda remains separate, a spiral of light across the void. And inside that spiral, a number almost too large to hold 1,000,000,000,000 stars. Each one a sun, each one possibly surrounded by worlds, by moons, by mysteries we'll never touch. If you could visit Andromeda, if you could somehow cross those 2.5 million light years, what would you see? You'd see a galaxy much like our own, a bright central bulge dense with older yellowish stars, spiral arms sweeping outward glowing with young blue-white stars, places where gas and dust are still collapsing into new light. And beyond the visible disk, a halo, a ghostly sphere of ancient stars and globular clusters, remnants of the galaxy's earliest days. But here's what you wouldn't see, at least not easily the majority of Andromeda's stars. Most of them are dim, small, red dwarf stars far smaller and cooler than our sun. They make up perhaps 70 or 80% of all stars in the galaxy, but they're so faint that even our best telescopes struggle to see them individually. This is one of the great challenges of counting stars. The ones we notice, the bright ones, the giants, they were the minority. The universe is full of quiet, humble stars, burning, slowly living, for trillions of years, far longer than stars like our sun. They are the silent majority. The ones that hold galaxies together, not with brightness, but with presence. How do you count what you can't see? That's the question we'll carry forward. Because the number 1 trillion isn't something we found by counting one by one. It's something we calculated, estimated, inferred from light and math and careful observation. It's a number built on trust in physics and patterns in the steady laws that seem to hold true across the universe. And maybe that's beautiful in its own way. We can't touch those stars. We can't visit them. We can't even see most of them. But we can know they're there. We can measure their influence. We can feel the weight of them through gravity, through light, through the gentle bending of space itself. Knowledge doesn't always mean seeing. Sometimes it means listening. Listening to what the universe is willing to tell us. So, tonight as you drift towards sleep, picture that soft light, that little cloud, that neighbor made of a trillion suns. Picture Edwin Hubble alone on a mountain, patient and persistent, finding the proof that expanded our universe forever. Picture Al-Sufi, 1,000 years earlier, recording something he didn't understand but honored anyway. And picture the stars themselves, not as numbers, not as data, but as light, ancient light, traveling through the dark, arriving here now, touching your eyes, your thoughts, your quiet wonder. We've only just begun. We've only just asked the question. In the moments ahead, we'll journey deeper. We'll explore how those stars were counted, why the number keeps changing, and what it means to live in a universe so full of light that even counting becomes a kind of poetry. But for now, let that question rest gently. How many stars are there in the Andromeda 1 trillion, give or take? Each one a story, each one a sun, each one unreachable and yet somehow right here with us. For most of human history, we didn't know galaxies existed. We looked up and saw stars, yes. The moon, planets wandering their slow paths. But galaxies, those vast islands of billions of suns, they were invisible to us. Not because they weren't there, but because we didn't yet have the eyes to see them, or the imagination to believe in them. And yet, Andromeda was always there, waiting. A faint smudge of light in the constellation that shares its name. Soft enough to miss if you weren't paying attention. Bright enough to notice if you were. The first people to record it didn't call it a galaxy. They called it a cloud, a mist, a mystery written in light. And for more than 1,000 years, that's all it was. A question hanging in the darkness, patient and unanswered. The earliest written record we have comes from the year 964 from a Persian astronomer named Abd al-Rahman al-Sufi. He lived in Isfahan in what is now Iran during the Islamic Golden Age, a time when scholars across the Middle East and Central Asia were preserving and expanding the knowledge of the ancient Greeks, Indians, and Babylonians. Al-Sufi compiled his observations into a book called Kitab Suwar al-Kawakib al-Thabita, or the Book of Fixed Stars. In it, he described a small, faint patch of light near the constellation Andromeda. He wrote that it appeared like a small cloud, no telescope, no camera, just his eyes, the dark desert sky, and centuries of astronomical tradition guiding his attention. Think about that. In 964 CE, a man looked up and saw something so faint, that most people would never notice it. He didn't know what it was. He had no way to measure its distance or understand its true nature, but he saw it. He recorded it. He made sure it would be remembered. Research shows that al-Sufi's observation wasn't just a lucky glance. He was part of a long tradition of careful sky watchers. Astronomers in the Islamic world had inherited star catalogs from Greek scholars like Ptolemy, but they didn't just copy them. They corrected them, refined them, added new observations. Al-Sufi's book included hand-drawn illustrations of constellations showing not just the brightest stars, but also these faint nebulous objects. He was mapping the invisible. But here's what's fascinating. Al-Sufi saw Andromeda with the naked eye. That means it's one of the very few galaxies visible without a telescope. In fact, under truly dark skies away from city lights, you can still see it the way he did. A soft, oval glow, gentle, quiet, easy to overlook. Most people today have never seen it. Light pollution has stolen that experience from billions of us. We live under skies so bright that even the Milky Way, our own galaxy, is hidden. But if you go somewhere dark enough somewhere the night still belongs to the stars, you can see what al-Sufi saw. You can connect across 1,000 years to that same faint light. Scientists suggest that Andromeda appears about 6 times wider than the full moon in the sky. But it's so dim that only the central core is visible to the naked eye. The outer regions, the spiral arms, the halo of stars, they're there but too faint for our eyes to detect without help. So, what we see is just a hint, a whisper of something much larger. After al-Sufi, the record goes quiet for centuries. Other cultures may have seen it. Indigenous astronomers around the world had sophisticated knowledge of the night sky. But written records, at least the ones that survived, are rare. Andromeda drifted through the centuries, seen, but not understood, a small mystery among countless others. Then, in the 1600s, everything changed. The telescope arrived. In 1609, Galileo Galilei turned a simple spyglass toward the heavens and saw things no human had ever seen. Mountains on the moon, moons orbiting Jupiter, countless stars invisible to the naked eye. The telescope didn't just magnify the universe, it shattered old certainties. It made the impossible visible. But here's something most people don't know. Galileo never saw Andromeda. Or, if he did, he never recorded it. Why not? It seems strange, doesn't it? He was obsessed with the sky. He drew what he saw with meticulous care. Yet, Andromeda, one of the brightest nebulae in the northern sky, doesn't appear in his notes. The answer is surprisingly simple. Galileo's telescope was designed to look at specific objects, planets, the moon, individual stars. It had a very narrow field of view. Andromeda is large and diffuse. It doesn't look like much through a small telescope, especially if you don't know what you're looking for. So, Galileo, despite revolutionizing astronomy, missed it entirely. It's a reminder that even the greatest minds have blind spots. Even the best tools have limitations. Discovery isn't just about looking. It's about knowing where to look and why. The first telescopic observation of Andromeda came later in 1612 from a German astronomer named Simon Marius. He described it as being like a candle flame seen through horn, a soft, steady glow. Marius didn't understand what he was seeing, but he noted its position and tried to describe its appearance as best he could. He compared it to familiar things, a candle, a flame, something gentle and persistent. For the next century and a half, astronomers cataloged these mysterious objects. They called them nebulae, from the Latin word for cloud or mist. Some were small and round. Others were elongated or spiral-shaped. No one knew what they were. Some thought they might be distant clusters of stars too far away to resolve individually. Others believed they were clouds of glowing gas, perhaps places where new stars were forming. In 1764, Charles Messier, a French astronomer, created his famous catalogue. Messier was a comet hunter. He spent his nights searching for new comets, those faint, fuzzy wanderers that sometimes appeared in the sky. But he kept getting frustrated. He'd spot something faint and fuzzy, get excited, observe it for a few nights, and then realize it wasn't moving. It wasn't a comet. It was just another one of those fixed nebulae sitting there, unchanging, tricking him into wasting his time. So, Messier made a list, a catalog of things that weren't comets, objects to avoid. Don't look at these, the list essentially said. They'll only disappoint you. Andromeda became number 31 on that list. Messier 31. M31. A beautiful distraction. It's ironic, isn't it? Messier created his catalog to help people ignore these objects. But in doing so, he created one of the most important reference lists in astronomy. Today, Messier objects are beloved. Galaxies, nebulae, star clusters. The things Messier considered nuisances are now considered treasures. Andromeda was M31, a cloud, a mystery, still unidentified. By the 1800s, telescopes had improved dramatically. Astronomers could see more detail. They could measure positions with greater accuracy. They could even begin to use photography, capturing light over long exposures, revealing things too faint for the eye to see. And the more they looked at nebulae like Andromeda, the more confused they became. Some nebulae clearly resolved into stars when viewed through powerful telescopes. Others remained stubbornly fuzzy. Were they all the same kind of object? Or were there different types of nebulae, each with its own nature? One common mistake people made, even professional astronomers, was assuming that everything in the night sky was part of our own galaxy. The Milky Way was enormous, after all. It stretched across the entire sky, a river of stars. Surely they thought everything we could see must be contained within it. The idea that there could be other galaxies, separate islands of stars, seemed unnecessary. Why multiply explanations when one would do? This assumption persisted well into the early 1900s. Even as telescopes revealed spiral structures in some nebulae, even as spectra showed strange velocities, many astronomers clung to the idea that the universe was just the Milky Way. Everything else was detail, everything else was internal, but a few observers weren't convinced. They noticed something peculiar. Spiral nebulae like Andromeda were never found along the plane of the Milky Way. They were always above or below. It scattered across the sky in a way that seemed independent of our galaxy's structure. If they were part of the Milky Way, why weren't they mixed in with everything else? In 1755, long before anyone had the evidence to prove it, the philosopher Immanuel Kant proposed a radical idea. He called it the island universe theory. What if he suggested those spiral nebulae weren't part of the Milky Way at all? What if they were separate galaxies, each one, a Milky Way in its own right, floating in the vast emptiness of space? It was a beautiful idea, poetic, almost unbelievable, and for more than 150 years it remained just that, an idea unproven and unprovable, until Edwin Hubble, until Cepheid variables, until the distance to Andromeda was finally measured. But we'll come to that soon. For now, think about the observers. Al-Sufi with nothing but his eyes and his careful notes. Simon Marius comparing a galaxy to candlelight. Charles Messier, frustrated and meticulous, making a list of things to ignore that became a map of wonders. And Immanuel Kant, a philosopher, imagining island universes long before anyone could prove they existed. Each of them saw Andromeda, or thought about it without knowing what it truly was. Each of them contributed a piece to the puzzle, and none of them lived to see the answer. That's the nature of discovery, isn't it? We build on fragments. We inherit questions. We pass them forward, hoping someone someday will find the key. For 1,000 years, Andromeda was a mystery, a little cloud, a candle flame, a spiral of light with no explanation. It didn't reveal itself easily. It waited patient and silent for the right question to be asked, for the right tools to be built, for the right mind to look at it and see not just what it appeared to be, but what it truly was. And when that moment finally came, when the truth was revealed, It wasn't just an answer, it was a transformation. The universe expanded. Our place in it shrank and grew at the same time. We became smaller, yes, but the night became infinitely richer. One little cloud became a trillion suns. One mystery became a million new questions. Have you ever noticed something for years without really seeing it? A tree on your street, a sound in the evening, something so familiar it becomes invisible. And then one day, for no particular reason, you actually look. You actually see. And it's like encountering it for the first time. That's what happened with Andromeda. It was always there, always visible. But it took 1,000 years of looking before we truly saw. The lesson isn't just about astronomy. It's about attention, about patience, about the difference between looking and seeing. The universe doesn't hide its wonders, but it doesn't shout about them either. It simply waits. And if we're willing to look carefully, to question what we think we know, to sit with mystery instead of rushing past it, the answers come, slowly, gently, in their own time. But the journey from mystery to understanding wasn't smooth. It was full of arguments, competing theories, brilliant minds convinced of opposite conclusions. Because that's how science works, not as a march toward truth, but as a conversation, sometimes a debate, sometimes a battle between different ways of seeing the same evidence. And nowhere was that more dramatic than in the great question of the early 20th century: was Andromeda inside our galaxy or impossibly beyond it? The answer would reshape everything. And it would take one of the greatest debates in the history of astronomy to set the stage for the final revelation. Imagine two brilliant minds standing on opposite sides of a question, so fundamental it would reshape our understanding of everything. One believes the universe is small, contained, knowable. The other believes it stretches beyond imagination, filled with islands of light we've only begun to discover. Both have evidence. Both have logic. Both are certain they're right. And only one can be. This wasn't philosophy. This was science at its most human. Two astronomers, one stage, and a question that would haunt the field for years. Is Andromeda part of our galaxy, or does it lie beyond it in the vast unknown? On April 26, 1920, the Smithsonian Museum of Natural History in Washington, D.C., hosted what would become known as the Great Debate. It wasn't called that at the time. The official title was far less dramatic: The Scale of the Universe. But history remembers it as a debate because that's what it was: a collision of ideas. A moment when astronomy stood at a crossroads and had to choose a direction. On one side stood Harlow Shapley, a young astronomer from Missouri, who had recently made groundbreaking discoveries about the size and shape of the Milky Way. On the other side was Heber Curtis, an experienced observer from California who had spent years studying spiral nebulae through telescopes. Both men were respected, both were brilliant, and both were about to argue for entirely different universes. If you find yourself drawn to these moments when science wrestles with uncertainty, when answers aren't clear and minds must remain open, you might want to stay connected. A gentle tap on the like button, a quiet subscription, and that small bell icon help more people discover these stories. Not to interrupt, but to invite. Because the best questions deserve to be shared. Shapley's argument was elegant. He had measured the size of the Milky Way by studying globular clusters, dense spheres of ancient stars that orbit the galactic center. By plotting their positions, he determined that the Milky Way was far larger than anyone had previously thought. Not thousands of light years across, but tens of thousands. Perhaps even 100,000 light years in diameter. A galaxy so vast it seemed to contain everything. If the Milky Way was that enormous, Shapley reasoned, why would we need other galaxies? Those spiral nebulae, those faint smudges of light like Andromeda, they could easily be part of our own galaxy. Perhaps they were just smaller structures within the Milky Way's outer regions. Perhaps they were clouds of gas destined to form new stars. Perhaps they were remnants of stellar explosions glowing quietly in the darkness. but separate galaxies, islands of billions of stars lying millions of light years away that seemed unnecessary, extravagant. The universe Shapley believed was grand enough with just one galaxy. He had evidence to support this view. Astronomers had observed novae, sudden brightenings of stars within some spiral nebulae. If those novae were similar to the ones observed in the Milky Way, and if they appeared equally bright, then the nebulae couldn't be very far away. They had to be relatively nearby, perhaps just tens of thousands of light years distant, well within the bounds of a large galaxy. Shapley also pointed to another piece of evidence. A Dutch astronomer named Adrian van Manen had measured the rotation of spiral nebulae. He claimed to have detected motion in their spiral arms over just a few years of observation. If true, this was damning evidence against the island universe theory. Why? Because if spiral nebulae were millions of light years away, their rotation would be imperceptibly slow. Even if they spun quickly, the vast distance would make any motion invisible over a human lifetime. But if Van Manen could see them rotating, they had to be close. They had to be small. They had to be part of the Milky Way. It was a strong argument, logical, supported by observation, and completely wrong. Curtis, on the other hand, believed in island universes. He looked at the same spiral nebulae and saw something different. He saw structure, patterns, similarities that suggested these weren't random clouds, but organized systems galaxies in their own right, lying far beyond the Milky Way's edge. Curtis had several key observations. First, he noted that spiral nebulae were never found along the plane of the Milky Way. They appeared above and below, it scattered across the sky, in a way that suggested they were external independent objects. If they were part of the Milky Way, you'd expect to see them mixed in with everything else concentrated along the galactic disk. But they weren't. They stood apart. Second, Curtis studied the spectra of spiral nebulae, the light broken into its component colors. Some of these nebulae showed Doppler shifts, suggesting they were moving at tremendous speeds, hundreds of kilometers per second. If they were part of the Milky Way, such speeds would be difficult to explain. But if they were separate galaxies moving through the larger universe under the influence of gravity, those velocities made sense. Third, and perhaps most compellingly, Curtis argued from analogy. If the Milky Way is a disc-shaped galaxy seen from the inside, and if we observe spiral nebulae that also appear disc-shaped when viewed, edge-on, isn't it reasonable to assume they're similar objects? That we're seeing other Milky Ways viewed from the outside? It was a powerful argument, but it lacked the one thing Shapley's argument seemed to have: direct measurement. Curtis was reasoning from patterns and probabilities. Shapley was citing numbers, observations, data from trusted colleagues. In the court of scientific opinion, data usually wins. The debate itself was less a debate and more two separate lectures. Shapley spoke first, presenting his case for a large Milky Way containing all known objects. Curtis followed, arguing for a universe filled with galaxies. There was no back and forth, no clash of ideas in real time. Just two visions presented and left to simmer. Historians suggest that neither man decisively won that night. The audience, composed of scientists and interested public members, left with mixed feelings. Some found Shapley more convincing. Others sided with Curtis. The question remained open, hanging in the air like those faint nebulae themselves, unresolved and tantalizing. But here's what makes the story so human, so poignant. Both men were partially right and partially wrong. Shapley was correct that the Milky Way was enormous, far larger than previously believed. But he was wrong about the spiral nebulae. Curtis was right that those nebulae were external galaxies. But he underestimated the size of the Milky Way, believing it to be much smaller than Shapley's measurements suggested. Science doesn't always reward the person who's most right. Sometimes it rewards the person who's right about the thing that matters most at that moment. And in this case, the question that mattered was, are there other galaxies? The answer, as we now know, is yes, emphatically yes. The universe contains not just one galaxy, but hundreds of billions, each one a separate island of stars drifting through the cosmic dark. Curtis's island universe theory was vindicated, but it would take new evidence, new tools, and a new observer to prove it beyond doubt. That observer was Edwin Hubble, and his tool was the 100-inch Hooker telescope atop Mount Wilson in California, the most powerful telescope in the world at the time. In October 1923, Hubble turned that telescope toward Andromeda. He wasn't the first to photograph it, but he was looking for something specific: Cepheid variable stars. These are stars that pulse in brightness with a regular rhythm. And here's the key: the period of that pulsation is directly related to the star's true luminosity. If you measure how long it takes a Cepheid to brighten and dim, you can calculate how intrinsically bright it is. And if you know how bright it truly is, and you measure how bright it appears from Earth, you can determine its distance. It's like seeing a lighthouse from a boat. If you know it's a lighthouse, not a candle, you can estimate how far away it must be, based on how dim it looks. Hubble found Cepheids in Andromeda. He measured their periods. He calculated their distances. And the result was staggering. Andromeda was nearly 900,000 light-years away. Later, refinements pushed that number even higher to about 2.5 million light-years, far, far beyond the edge of the Milky Way, far beyond anything Shapley's model could contain. Andromeda wasn't part of our galaxy. It was a galaxy, a separate universe of stars. When Hubble announced his findings, the astronomical community was stunned. Some resisted. Some questioned the measurements, but the evidence was too strong, too clear, too carefully gathered. Within a few years, the debate was over. The island universe theory was confirmed. The cosmos expanded overnight. Shapley, to his credit, accepted the new evidence. He didn't cling to his old model. He adjusted his understanding. That's the mark of a true scientist, not the refusal to be wrong, but the willingness to change when better evidence arrives. Curtis didn't live to see the full vindication of his ideas. He died in 1942, long after Hubble's discovery, but before the true scale of the universe was fully understood. But his instincts were right. His pattern recognition was sound. He looked at the evidence and saw beyond the obvious imagining, a cosmos far grander than the one most people were willing to believe in. And what about Van Maenen's measurements? The ones that showed spiral nebulae rotating? They were wrong. Errors in technique, perhaps wishful thinking, subtle biases in how he analyzed photographic plates. It happens. Even careful observers can make mistakes, especially when the measurements are at the very edge of what's possible with the technology of the time. Science corrects itself, but not always quickly, and not always without cost. The great debate is often taught as a simple story: one person right, one person wrong. But the truth is more complicated, more interesting. Shapley made real discoveries about the Milky Way's size. Curtis correctly identified the nature of spiral nebulae. Van Maenen made honest mistakes that temporarily misled the field. And Hubble, standing on all their shoulders, found the evidence that settled the question. That's how science works, not as a competition with clear winners and losers, but as a conversation across time, where each voice adds something, even the ones that turn out to be mistaken. Have you ever been certain of something, only to discover later you were looking at it from the wrong angle? That moment of realization when the world reshapes itself around new understanding, it's disorienting and exhilarating at once. That's what the astronomical community experienced in the 1920s. The universe they thought they knew dissolved. A new one, vaster and stranger, took its place. And at the center of that revelation was Andromeda, that little cloud, that faint smudge, that object people had seen for 1,000 years without understanding. Suddenly, it wasn't a mystery anymore. It was a neighbor, a trillion suns bound together by gravity spinning slowly through the void. The question shifted. It was no longer, what is Andromeda? It became, how many stars does it hold? What is its structure? What can it teach us about our own galaxy and about the universe itself? The answers to those questions would take decades more to uncover. And they would require not just better telescopes, but better mathematics, better physics, and a willingness to embrace the strangeness of a cosmos that refused to be simple. But we're getting ahead of ourselves. Before we can count the stars, before we can measure the trillion points of light that make up Andromeda, we need to understand what a galaxy truly is. Not just as a concept, but as a structure, a living, evolving system of stars and gas and dust and gravity all moving together in an intricate dance that spans hundreds of thousands of light years. That understanding, that deep knowledge of galactic architecture, is what comes next. And it's what finally makes counting possible. A galaxy isn't just a random scatter of stars thrown across the darkness. It's a structure, a pattern, an architecture built by gravity over billions of years, shaped by rotation, by collisions, by the slow accumulation of gas and dust, falling inward, spiraling, condensing into new light. If you want to count the stars in Andromeda, you first need to understand how they're arranged, where they live, how they move, because a galaxy isn't a static painting. It's a living system, breathing slowly across cosmic time. Think of it this way. If someone asked you how many people live in a city, you wouldn't just guess. You'd need to know the city's layout. Where are the dense neighborhoods? Where are the suburbs? Where do people gather? And where do they spread thin? A galaxy is no different. It has structure. It has neighborhoods. And understanding that structure is the first step toward counting its inhabitants. When astronomers look at Andromeda, they don't see a trillion individual stars. They can't. Even the most powerful telescopes can only resolve a fraction of them. What they see instead is light, patterns of brightness and darkness, regions where stars cluster densely, and regions where they thin out. From those patterns, from the way light is distributed across space, they can begin to map the galaxy's architecture. Before we go further into that map, if these quiet explorations of the cosmos bring you a sense of calm, a moment of wonder before sleep, perhaps you'd like to stay a while longer. A soft tap on the like button, a gentle subscription, and that little bell can help this space grow, reaching others who find comfort in the slow unfolding of cosmic mysteries. Not a demand, just an invitation. Now, let's continue. Andromeda, like our own Milky Way, is a spiral galaxy. That term might sound simple, but it contains multitudes. A spiral galaxy isn't just one thing. It's a collection of distinct regions, each with its own character, its own population of stars, its own story. At the very center lies the bulge. This is the heart of the galaxy, a dense, roughly spherical concentration of stars. If you could visit the bulge, you'd find yourself surrounded by ancient light. These are old stars formed billions of years ago when the galaxy was young. They're mostly yellow and red, cooler than our sun, running low on fuel, but still burning steadily. The bulge is crowded. Stars here are packed far more closely than in our neighborhood of the Milky Way. If Earth orbited a star in Andromeda's bulge, the night sky would be dazzling, filled with thousands of bright stars, some close enough that their light would cast faint shadows. Research shows that the bulge of Andromeda contains roughly a quarter of the galaxy's total stellar mass. That's an enormous concentration. Billions upon billions of stars all orbiting the galactic center in complex overlapping paths. Some orbit quickly, some slowly. Some move in elliptical loops, others in more circular trajectories. The result is a kind of stellar chaos, but a stable chaos held together by gravity's patient grip. At the very core of the bulge, invisible but undeniable, sites a supermassive black hole. Astronomers estimate its mass at around 100 to 200 million times the mass of our sun. It's not feeding actively right now, not devouring gas and dust in a blaze of radiation like some galactic cores do. It's quiet, dormant, but it's there, warping space around it, anchoring the galaxy's rotation. Moving outward from the bulge, you encounter the disk. This is where most of the galaxy's visible structure lives. The disk is flat thin compared to its width stretching across more than 200,000 light-years of space. It's here that you find the spiral arms, those graceful curves of light that give spiral galaxies their name. Here's something people often misunderstand about spiral arms. They're not permanent structures. They're not like the arms of a starfish fixed in place. Instead, they're density waves regions where stars and gas temporarily pile up as they orbit the galactic center. Think of traffic on a highway. Cars move at different speeds, but sometimes a slowdown forms a clump of vehicles that persists even as individual cars pass through it. Spiral arms work the same way. Stars drift into them, linger for a while, then drift out again. The arm remains, but its contents constantly change. Why do spiral arms matter when counting stars? Because they're where new stars are born. The density wave compresses gas and dust, triggering gravitational collapse, igniting fusion. Young, hot blue stars light up the spiral arms, making them the brightest features of the galaxy. But these stars are a minority. They're spectacular, but short-lived. Most stars, the quiet, dim, long-lived ones, exist outside the spiral arm, scattered throughout the disk. Scientists suggest that Andromeda has at least 2 major spiral arms, possibly more, depending on how you define them. Some regions of the disk show subtle structures, hints of additional arms or spurs, but the details are hard to map from our vantage point. We're looking at Andromeda at an angle not face-on, which makes interpretation tricky. Imagine trying to understand the layout of a building when you can only see it from one corner. You can infer a lot, but some details remain hidden. The disk doesn't end abruptly. It fades gradually, thinning out as you move farther from the center. Stars become sparser. Gas becomes scarce. But the galaxy doesn't stop. Beyond the visible disk lies the halo. The halo is enormous, a roughly spherical cloud of material surrounding the entire galaxy. It extends far beyond the disk, reaching out hundreds of thousands of light years, perhaps even farther. We can't see most of it. The stars in the halo are old, dim, and spread incredibly thin. But they're their ancient relics from the galaxy's earliest days, orbiting in long, looping paths that carry them far above and below the disk before swinging them back again. Within the halo, astronomers have identified globular clusters, dense spheres of stars that orbit the galaxy like moons orbit a planet. Each globular cluster contains tens of thousands to millions of stars, all bound together by gravity. Andromeda has more than 450 known globular clusters, possibly many more waiting to be discovered. These clusters are among the oldest objects in the galaxy time capsules, preserving information about conditions in the early universe. Comparing Andromeda to the Milky Way helps us understand both. Our galaxy is also a spiral, also has a bulge, a disk spiral, arms, and a halo. But there are differences. Andromeda is larger. Its disk stretches farther. Its total mass, including stars and gas and the mysterious dark matter that pervades the halo, is estimated to be about twice that of the Milky Way. If Andromeda is the big sibling, the Milky Way is the slightly smaller companion, still grand but outmatched in sheer scale. One common mistake people make is assuming all galaxies are the same. They're not. Some galaxies are elliptical, smooth, and featureless, lacking the dramatic spiral structure. Others are irregular, chaotic tangles of stars with no clear organization. Spiral galaxies like Andromeda represent a specific evolutionary path, a result of rotation, and the gradual accumulation of gas into a flattened disk. Each type of galaxy has its own population of stars, its own history, its own character. Understanding Andromeda's structure also helps us understand where stars of different types live. The bulge, as we said, is dominated by old red stars. The disk, especially. The spiral arms hosts younger, hotter blue stars. The halo contains the oldest stars of all metal-poor relics, from a time when the universe itself was simpler, composed mostly of hydrogen and helium, with only traces of heavier elements. This distribution matters for counting. If you want to estimate the total number of stars you need to account for each region separately, you can't just look at the brightest parts and extrapolate. The The bright young stars in the spiral arms contribute most of the light, but they're far outnumbered by the dim ancient stars scattered throughout the bulge disk and halo. It's like estimating the population of a city by only counting the people in the shopping district. You'd miss the vast majority living quietly in residential areas. Astronomers use a variety of techniques to map this structure. They measure the distribution of light at different wavelengths. Ultraviolet light reveals hot young stars. Infrared light penetrates dust and reveals cooler older stars. By combining observations across the electromagnetic spectrum, they build a more complete picture. They also study the motion of stars. By measuring Doppler shifts, tiny changes in the wavelength of starlight caused by motion toward or away from us. Astronomers can determine how stars are orbiting the galactic center. This tells them about the mass distribution, about where the gravity is strongest, about the invisible dark matter that holds everything together. Dark matter, by the way, is another key piece of galactic architecture. We can't see it. It doesn't emit light, but it has mass, and that mass exerts gravity. Scientists believe that the halo of Andromeda, like the halo of the Milky Way, is dominated by dark matter. It outweighs all the visible stars combined, providing the gravitational scaffolding that keeps the galaxy from flying apart as it rotates. Without dark matter, the outer regions of the galaxy would be rotating too fast. The visible mass, the stars and gas, wouldn't generate enough gravity to hold them in. They'd drift away into the cosmic void. But they don't. They stay bound. And the only explanation that fits the observations is an enormous halo of invisible mass surrounding and permeating the galaxy, patient and silent. If Andromeda were a city, the bulge would be the dense downtown, all skyscrapers and crowded streets. The disk would be the main urban sprawl with neighborhoods and parks and the occasional bright commercial district. The halo would be the distant countryside, sparsely populated but vast, stretching far beyond the city limits. And dark matter. That would be the foundation, the bedrock, invisible but essential, holding everything up. This architecture, this layered structure, is what we're trying to count. Not just stars in the abstract, but stars in specific places, stars of specific types, stars at different stages of their lives. Because a trillion is just a number, what matters is understanding what that number represents. A trillion suns, yes. But also a trillion stories, a trillion points of light each with its own temperature, its own brightness, its own history. Have you ever tried to estimate something vast by breaking it into smaller pieces? Maybe you've looked at a crowded room and guessed the number of people by sectioning it, mentally counting one section and multiplying. That's exactly what astronomers do with galaxies. They divide Andromeda into regions, estimate the stellar population in each region, and sum the results. It's not perfect. There are uncertainties, but it's the best we can do. One of the beautiful ironies of astronomy is that we understand distant galaxies better than we understand our own. Why? Because we can see them from the outside. We can observe their full structure, their spiral arms, their bulges, their halos all at once. The Milky Way. By contrast, we're stuck inside. We're trying to map our home from within, like drawing a floor plan of a house while sitting in a closet. Andromeda gives us a reference point, a comparison, a way to check our assumptions about galactic structure. As telescopes improve, as computational models become more sophisticated, our understanding of Andromeda's architecture deepens. We find faint streams of stars in the halo, evidence of smaller galaxies that Andromeda consumed long ago, their stars now scattered and absorbed. We detect subtle warps in the disk signs of gravitational interactions with nearby galaxies. We map individual star-forming regions in the spiral arms, watching as hydrogen clouds collapse and ignite. Each detail adds to the picture. Each observation refines the map. And each refinement brings us closer to answering that central question: how many stars? But before we can answer that, we need to talk about the math, the methods, the tools astronomers use to turn observations of light into estimates of population. Because you can't count a trillion stars one by one. You need shortcuts. You need assumptions. You need a deep understanding of how stars emit light, how that light travels through space, and how we can interpret it from millions of light years away. That's where the science becomes both more abstract and more beautiful, where numbers and physics merge into something almost poetic. And that's where we're headed next. How do you count something you can't reach? How do you measure what you can't touch? How do you determine the population of a city when you're standing millions of miles away, unable to see individual faces, unable to knock on doors, unable to do anything but collect the light that drifts toward you through the darkness? This is the challenge astronomers face. And the solution isn't found in bigger telescopes alone. It's found in mathematics and physics, in the careful interpretation of light itself. Counting the stars in Andromeda is at its heart an act of translation. We observe brightness, we measure color, we analyze spectra, and from those observations, we infer mass distance population. It's indirect, it's elegant, and it's the only way we have. Imagine standing on a hill at night, looking down at a distant city. You see lights, thousands of them, but you can't count individual buildings. You can't see individual people. What you can do is estimate. You notice clusters of brightness patterns in the distribution of light. You know that certain types of light, streetlights, perhaps have a predictable brightness. If you can identify those, measure how dim they appear from your hilltop, you can calculate distance. And once you know distance, you can begin to estimate density, population, structure. Astronomy works the same way. Light is the messenger. Math is the interpreter. If you find yourself drawn to the way science turns observation into understanding the way small pieces of information build into something vast and comprehensible, perhaps you'd like to stay connected to this journey. A gentle, like a quiet subscription, and that little notification bell help this space reach others who seek knowledge told softly without rush. Now, let's explore the mathematics of starlight. The most direct way to count stars would be to point a telescope at a galaxy and count them one by one. And for nearby galaxies in small regions, astronomers do exactly that. They take long exposure photographs, identify individual stars, catalog them. But Andromeda contains a trillion stars. Even if you could resolve every single one, which you can't counting them individually, would take lifetimes. You'd need a different approach for each region, adjusting for crowding, for dust, obscuring your view, for the limits of your instruments. It's not impossible, but it's impractical. So instead, astronomers use what's called the mass-to-light ratio method. Here's how it works. First, you measure the total amount of light coming from the galaxy. Not just visible light, but infrared ultraviolet across the spectrum. You add it all up, correcting for distance, for dust, absorption, for any factors that might distort the measurement. That gives you the galaxy's total luminosity, how much energy it's radiating into space. Next, you need to know how much light an average star produces. This is where things get tricky. Stars aren't all the same. A massive blue star emits thousands of times more light than our sun. A tiny red dwarf emits a fraction of the sun's light. So, what's average astronomers use what they know about stellar populations, the typical mix of star types in galaxies like Andromeda, to estimate an average stellar mass and an average luminosity per unit mass. This ratio, luminosity to mass, becomes a key tool if you know the total luminosity and you know the average luminosity per star. You can estimate the number of stars. It's like estimating the number of candles in a dark room by measuring the total light and knowing how bright each candle is. Not perfect, but reasonable. Research shows that for galaxies like Andromeda, the mass-to-light ratio isn't constant across the entire structure. The bulge filled with old red stars has a different ratio than the disk, which contains more young blue stars. So astronomers divide the galaxy into regions, calculate separately for each, then sum the results. This accounts for the variations, making the estimate more accurate. But there's a complication. Not all the mass in a galaxy is in stars. Some is in gas and dust, the raw material for future star formation. Some is in stellar remnants, white dwarfs and neutron stars, and black holes, the corpses of stars that no longer shine. And a huge amount is in dark matter, invisible but gravitationally significant. So, when astronomers measure the total mass of the galaxy through its gravitational effects, through the rotation curves that show how stars orbit the center they're seeing, more than just stars. To isolate the stellar mass, they need to subtract the other components. They estimate the gas mass by observing hydrogen emissions. They estimate the dark matter halo through models of galactic rotation. What remains is the stellar mass, and from that, they can estimate the number of stars. Another method involves photometry, the precise measurement of brightness. Astronomers take images of Andromeda in multiple wavelengths, each wavelength sensitive to different types of stars. Hot young stars shine brightly in ultraviolet. Cool old stars dominate in infrared. By comparing the brightness at different wavelengths, astronomers can infer the stellar population. They can estimate how many stars of each type exist, even if they can't see them individually. Spectroscopy adds another layer of detail. When you split starlight into its component colors, you see absorption lines, dark bands, where specific elements absorb specific wavelengths. The pattern of these lines tells you the star's temperature, its chemical composition, its motion. By taking spectra of many stars in Andromeda, or even of the integrated light from entire regions, astronomers can determine the dominant stellar types and refine their population estimates. There's also the luminosity function method. Astronomers study the distribution of stellar brightness in regions where they can resolve individual stars. They count how many bright stars, how many medium stars, how many faint stars they see in a sample area. Then they fit that distribution to a mathematical function, a curve that describes how common stars of different brightnesses are. Once they have that function, they can extrapolate to the entire galaxy. If the sample is representative, the function should hold everywhere, allowing them to estimate the total stellar population. Each of these methods has uncertainties. Measurements have error bars. Models make assumptions. But when multiple methods agree, when different approaches converge on similar numbers, confidence grows. And for Andromeda, that convergence points toward 1 trillion stars. One common mistake people make is assuming that because we can't see individual stars, we don't really know anything. But that's not true. We know a lot. We know the total mass. We know the light distribution. We know the chemical composition. We know the rotation speed. All of these measurements constrain the possibilities. They narrow the range of plausible answers. The number might not be exact, but it's not a wild guess. It's an informed estimate built on decades of careful observation and rigorous mathematics. Here's an analogy. Imagine you're trying to estimate the number of grains of sand on a beach. You can't count them individually, but you can measure the beach's area. You can dig up a small sample and count how many grains fit in a cup. You can estimate the average depth of the sand. With those measurements, you can calculate a reasonable approximation. It won't be perfect. Some areas might be deeper, some shallower. Some sand might be coarser, some finer. But you'll be in the right ballpark. That's what astronomers do with galaxies. The estimate for Andromeda, around 1 trillion stars, comes with an uncertainty of perhaps 20 to 30%. That means the true number could be anywhere from 700 billion to 1.3 trillion. That's a huge range in absolute terms, hundreds of billions of stars. But in relative terms, it's actually quite precise. We're not off by orders of magnitude. We're refining the details. Why does the number keep changing slightly as new studies are published? Because our tools improve, because our models become more sophisticated, because we find new ways to account for faint stars, for dust, for the complexities of stellar populations. Each refinement brings us closer to the truth, even if we never reach it exactly. Scientists suggest that one of the biggest sources of uncertainty is the faint end of the stellar population. The smallest, dimmest stars, the red dwarfs, are incredibly hard to detect. They contribute very little light, so they don't show up strongly in luminosity measurements. But they're numerous, possibly making up the majority of all stars. If you underestimate how many red dwarfs there are, you underestimate the total stellar population. This is where infrared observations become crucial. Red dwarfs shine more brightly in infrared than in visible light. By observing Andromeda with infrared telescopes like Spitzer or WISE astronomers can detect stars that would be invisible in optical wavelengths. This helps them refine their counts, accounting for the silent majority of stars that populate the galaxy, but rarely make their presence obvious. Think about the elegance of this process. We're standing on a small planet orbiting an average star in an average location within one galaxy. And from that vantage point, we're measuring the population of another galaxy 2.5 million light years away. We're translating photons, particles of light that have traveled for millions of years into numbers, into knowledge, into understanding. It's astonishing when you pause to consider it. There's also the question of what counts as a star. Do brown dwarfs count? These are objects that form like stars, but never quite ignite full hydrogen fusion. They're more massive than planets, but less massive than true stars. They glow faintly from leftover heat, but they don't shine the way stars do. Should they be included in the count? Different studies handle this differently, which is another reason estimates vary. And what about binary stars? Two stars orbiting each other so closely, they appear as a single point of light. From our distance, we can't always tell if we're seeing one star or two. Astronomers use statistical models to estimate the binary fraction, the percentage of stars that are actually multiple systems. They adjust their counts accordingly. But it's another layer of complexity, another source of uncertainty. Despite all these challenges, the methods work. We can cross-check them against each other. We can test them on nearby galaxies where we can resolve more stars individually. We can compare the results with theoretical models of galaxy formation and evolution. And when everything aligns, when observation theory and mathematics all point in the same direction, we trust the result. Have you ever solved a puzzle by working backward from the answer? That's a bit like what astronomers do. They know certain physical laws must hold. Stars must obey gravity. They must follow predictable fusion processes. They must emit light according to their temperature and size. These laws are universal as far as we know. So astronomers use them as constraints, as guideposts, ensuring their estimates remain physically plausible. One particularly beautiful method involves comparing Andromeda to our own Milky Way. We know our galaxy better because we're inside it. We can count stars more directly in our local neighborhood than scale up. If Andromeda is roughly twice as massive as the Milky Way, and if the stellar populations are similar, we'd expect it to have roughly twice as many stars. This scaling by analogy isn't perfect, but it provides a sanity check, a way to ensure our methods aren't wildly off. The number 1 trillion isn't arbitrary. It's not pulled from thin air. It's the result of countless hours of observation, thousands of scientific papers, decades of refinement. It represents the collective effort of astronomers around the world, each contributing a piece, each refining the picture. And while the exact number might shift as new data arrives, the scale, the magnitude remains. Counting stars in Andromeda isn't about precision for its own sake. It's about understanding galaxy formation, stellar evolution, the history of the universe itself. Each star is a data point. Each population tells a story about when and how stars formed, about the conditions in the early galaxy, about the processes that shape cosmic structures. The count is the beginning, not the end. It's the foundation for deeper questions. But even as we refine our methods, even as our telescopes grow more powerful and our models more sophisticated, there's a limit. Some stars will always remain invisible. Some will be too faint, too distant, too obscured by dust. The final count, the true count, might never be known with absolute certainty. And maybe that's okay. Maybe the beauty isn't in the final answer, but in the process, in the elegant dance between observation and inference between light and mathematics. But there's another reason the count remains uncertain, another population hiding in plain sight, stars so dim, we're only beginning to grasp how many there truly are. And understanding them changes everything. What if I told you that most of the stars in Andromeda are invisible? Not because they're hidden behind dust or too far away, but because they're simply too dim to see. They exist in the billions, perhaps hundreds of billions, quietly burning their fuel at such a low temperature, such a feeble brightness that even our most powerful telescopes struggle to detect them. They are the red dwarfs, the silent majority, the stars that hold galaxies together not through brilliance, but through sheer persistence. When we picture a star, we often imagine something like our sun, bright yellow, steady. Or maybe we think of massive blue giants blazing hot and luminous. But the truth is, most stars are nothing like that. Most stars are small, cool red, and so faint that if you replaced our sun with one, Earth would freeze solid within days. These are the stars that dominate Andromeda's population. And they're the reason counting stars is so much harder than it seems. Understanding red dwarfs changes everything. It changes how we count. It changes what we think a typical star looks like. It changes our sense of what's common and what's rare in the universe. Because what shines brightest isn't always what matters most. If these quiet revelations about the hidden architecture of the cosmos bring you a sense of peace, a feeling that the universe is richer than it first appears, you might want to stay with us a little longer. A gentle, like a soft subscription, and that small bell icon help these stories reach others who find comfort in the unhurried unfolding of scientific wonder. Now, let's drift into the world of the stars that don't seek attention. Red dwarfs are small. The least massive red dwarfs weigh only about 8% of the sun's mass. They're not much larger than Jupiter, though far denser, their core is hot enough to sustain hydrogen fusion. The most massive red dwarfs reach about half the sun's mass. Beyond that, a star becomes orange, then yellow, then white, then blue as mass and temperature increase. But the vast majority of stars never cross that threshold. They remain red, they remain small, they remain dim. Scientists suggest that red dwarfs make up roughly 70 to 80% of all stars in the universe. Some estimates push that number even higher. In Andromeda, that means out of 1 trillion stars, perhaps 700 or 800 billion are red dwarfs. They're everywhere. They dominate the stellar census. Yet, for most of human history, we didn't know they existed. Why? Because they're faint. A typical red dwarf emits only about 1,000th to 1/10,000th the light of our sun. Some are even dimmer. If you placed one where the sun is now, it would appear about as bright as a full moon. Not enough to warm the earth. Not enough to sustain life as we know it. Just a faint reddish glow in the sky. From 5 million light-years away, at Andromeda's distance, a red dwarf is nearly impossible to see individually. Even the Hubble Space Telescope, with all its sensitivity, can only detect the brightest red dwarfs in Andromeda's nearest regions. The rest blend into a diffuse background, contributing to the galaxy's overall glow, but remaining individually invisible. This creates a problem for astronomers trying to count stars. If you can't see most of the stars, how do you know they're there? How do you include them in your estimate? The answer lies in inference and statistical modeling, in understanding the physics of star formation well enough to predict what you can't observe. Here's what we know. Stars form from clouds of gas and dust that collapse under their own gravity. As the cloud fragments and condenses, it forms clumps of different masses. The distribution of those masses follows a pattern called the initial mass function, or IMF. Observations of nearby star-forming regions, places where we can actually resolve individual stars, show that for every massive star that forms, dozens or hundreds of low-mass stars form alongside it. The IMF isn't random. It seems to be remarkably consistent across different environments, different galaxies, different epochs of cosmic history. Massive stars are rare. Medium stars like our Sun are less common than you might think. And small stars, red dwarfs, are abundant. The curve slopes steeply. The smaller the mass, the more stars you get. This pattern appears to be universal, a fundamental feature of how gravity and gas physics work together. By applying the IMF to Andromeda, astronomers can estimate how many red dwarfs must exist even if they can't see them. They observe the massive stars, which are bright and easy to detect. They count the medium stars, which are also visible. Then they use the IMF to extrapolate downward, calculating how many faint stars must accompany the bright ones. It's indirect, but it's based on solid observational evidence from regions where we can check the predictions directly. Research shows that this method works. In nearby galaxies where we can resolve more individual stars, the predicted number of red dwarfs matches the observed count. This gives astronomers confidence that the same approach is valid for Andromeda. But why are red dwarfs so common? The answer has to do with how star formation works. When a gas cloud collapses, it doesn't form just one star. It fragments into many pieces, and those pieces have a range of masses. Most fragments end up small simply because there's a limit to how much mass any one fragment can accumulate before nearby gravity and turbulence disrupt the process. It's easier for the cloud to make many small stars than a few large ones. So nature favors red dwarfs. Think of it like raindrops. When clouds release water, they form many small drops and only a few large ones. The distribution isn't random. It's shaped by the physics of surface tension, gravity and air resistance. Star formation is similar. Gravity, turbulence, magnetic fields, and radiation pressure all influence how gas clumps together. The result is a predictable distribution weighted heavily toward small masses. Another fascinating aspect of red dwarfs is their longevity. Massive stars burn through their fuel, quickly living only millions of years before exploding as supernovae. Our sun will last about 10 billion years. But red dwarfs burning their hydrogen slowly and efficiently can survive for trillions of years. Some of the smallest red dwarfs will outlive the current age of the universe by a factor of 100 or more. This means every red dwarf that has ever formed is still alive. None have died yet. The universe simply isn't old enough. Every red dwarf born in the early days of Andromeda, when the galaxy was young and chaotic, is still burning today, a witness to billions of years of history. Imagine that. Stars that remember the beginning. Stars that will outlast almost everything else. Stars so patient they make geological time look like an eye blink. But their dimness is both a strength and a challenge. Red dwarfs are stable, long-lived, incredibly common. But they're also hard to study. Even nearby red dwarfs, just a few light years from Earth, are faint enough that we need sensitive instruments to observe them in detail. For red dwarfs in Andromeda, we mostly have to infer their existence and properties from models. This is where infrared astronomy becomes essential. Red dwarfs emit most of their energy in the infrared wavelengths longer than visible light. To the human eye, they'd appear deep red, almost invisible. But infrared detectors see them more clearly. Telescopes like Spitzer and the James Webb Space Telescope can observe in infrared, allowing astronomers to study red dwarf populations in ways that were impossible with optical telescopes alone. By observing Andromeda in infrared, astronomers have refined their estimates of the red dwarf population. They've confirmed that these stars are indeed abundant, filling the disk and halo, contributing significantly to the galaxy's total mass, even though they contribute little to its light. Here's a common misconception. People often assume that the brightest stars are the most important, that luminosity equals significance. But in terms of mass, in terms of numbers, in terms of gravitational influence, red dwarfs dominate. They're the foundation. The massive luminous stars are the exception, the brief fireworks that capture our attention, but don't represent the norm. It's like a city where a few skyscrapers dominate the skyline, but most of the population lives in small houses spread across quiet neighborhoods. The skyscrapers are visible from miles away. They define the city's silhouette, but the houses unseen individually hold most of the people, most of the stories, most of the life. One particularly intriguing red dwarf is Proxima Centauri, the closest star to our Sun. It's only 4.24 light years away, practically next door in cosmic terms. Yet, it's so faint that it wasn't discovered until 1915, and it's invisible to the naked eye despite being our nearest stellar neighbor. If Proxima Centauri were at Andromeda's distance, we wouldn't detect it at all with current technology. And Proxima isn't even among the faintest red dwarfs. Some are dimmer still. This gives you a sense of the challenge. If we can barely study red dwarfs in our own cosmic backyard, how can we claim to know how many exist in a galaxy too? 5 million light years away. The answer is that we don't count them directly, we infer them. We use physics statistics and observations of brighter stars to build a model. The model isn't perfect, but it's grounded in reality, tested against nearby examples, refined over decades. Scientists also study the integrated light of entire regions in Andromeda. Even if individual red dwarfs are invisible, their collective glow contributes to the total. By analyzing the color and spectrum of that light, astronomers can determine what mix of stellar types must be present. If the light is too red, there are too many cool stars. If it's too blue, there are too many hot stars. By matching the observed spectrum to models of stellar populations, they can estimate the ratio of red dwarfs to other stars. Another method involves looking at the motions of stars in the galaxy. Red dwarfs have mass, and that mass exerts gravity. Even if you can't see them, you can feel their gravitational influence on the stars you can see. By studying how visible stars move, how the galaxy rotates, astronomers can infer the total stellar mass, including the contribution from invisible red dwarfs. All of these methods converge on the same conclusion: red dwarfs are abundant. They're the majority. And any estimate of Andromeda's stellar population that doesn't account for them is dramatically wrong. Here's a question to consider. If most stars are too dim to see, what else might we be missing? What other populations, what other phenomena exist just below our detection threshold, shaping the universe in ways we're only beginning to understand? Red dwarfs remind us that visibility isn't the same as existence. The universe is full of things we can't see but must learn to recognize through indirect means. There's a certain humility in this. We build magnificent telescopes, peer across millions of light years, resolve details in distant galaxies, and still most of what's there remains hidden. Not because it's mysterious or exotic, but simply because it's small and quiet. The universe doesn't make everything easy to see. It asks us to look carefully, to think deeply, to trust in methods that go beyond direct observation. Red dwarfs also raise questions about planets and life. Many red dwarfs host planets. Some of those planets orbit in the habitable zone, the region where temperatures might allow liquid water. Could life exist on such worlds? It's possible, though. The conditions would be strange. Red dwarf planets in the habitable zone orbit very close to their stars, closer than Mercury is to our Sun, because the star is so dim. They're likely tidally locked one side, always facing the star the other in eternal darkness. The star itself might flare unpredictably, bathing the planet in radiation. But life, if it exists, might adapt. It might thrive in conditions we'd consider extreme. And if red dwarfs make up most of the stars, and if even a small fraction host habitable planets, the universe could be far richer in potential life-bearing worlds than we ever imagined. Most of it would orbit stars we can barely see, worlds we'd struggle to detect, life evolving quietly in the dim red glow of stars that will burn long after our sun has died. It's a thought to drift with, that the universe's story isn't written in brightness, that the majority, the quiet persistence of countless small stars, matters more than the spectacular few, that what endures isn't always what shines. In Andromeda, those red dwarfs are there, hundreds of billions of them, burning slowly, waiting patiently, holding the galaxy together with their combined mass, their steady gravitational pull. They don't demand attention. They don't blaze across the sky. They simply are. And in their humble existence, they outnumber all the brilliant stars we celebrate. Understanding them changes the count. It changes the story. It changes what it means to say Andromeda contains 1 trillion stars. Because that number, that vast, almost incomprehensible number, is mostly made of stars we'll never see individually. Stars that exist not to be seen, but to be inferred, to be understood, to be honored for what they are, the quiet foundation of everything. But beyond the red dwarfs, beyond the stars we've discussed, there's the number itself, the final answer astronomers have converged upon after decades of observation and calculation. And understanding what that number truly means, where it comes from, and why it matters, is where our journey leads next. 1 trillion. It's a number so large it loses meaning. Our brains aren't built to comprehend it. We can say the words, write the digits, but truly grasping what 1 trillion represents, that's something else entirely. And yet that's the answer. That's how many stars astronomers believe exist in the Andromeda Galaxy. 1 trillion suns, give or take a few hundred billion, all bound together by gravity, all spinning slowly through the cosmic dark. But where does this number come from? Who decided it? And what does it actually mean? 1 trillion isn't just big, it's beyond big. It's the kind of number that makes you pause, that makes you question whether you heard correctly. 1 trillion stars, each one potentially surrounded by planets, each one a furnace of nuclear fusion, each one with its own story, its own beginning, its own eventual end. How do we even begin to wrap our minds around that? Numbers, this vast need context. They need comparison. They need metaphors that bring them down to human scale, even if just for a moment. Because understanding isn't just about knowing the number. It's about feeling what the number represents. If you find yourself drawn to these moments when science reveals something so vast, it humbles us when numbers become doorways into wonder. Perhaps you'd like to stay a while. A gentle, like a quiet subscription, and that small bell help these explorations reach others who seek knowledge told softly, who find beauty in the mathematics of the cosmos. Now, let's explore what 1 trillion truly means. The number 1 trillion comes from decades of research, from observations made by space telescopes and ground-based observatories, from calculations refined over and over as new data arrived. It's not a guess. It's not a rough estimate plucked from thin air. It's the result of careful, methodical science built on the foundation of everything we've discussed so far. Galactic structure, stellar populations, luminosity measurements, mass-to-light ratios, and the recognition that most stars are too faint to see directly. The European Space Agency NASA and astronomers using the Hubble Space Telescope have all contributed to this estimate. Different studies approach the question from different angles, using different methods, and they converge on similar numbers. Some studies suggest 900 billion stars. Others push toward 1.2 trillion. The consensus settles around 1 trillion, with an uncertainty of perhaps 20 to 30% in either direction. That uncertainty is important to acknowledge. We're not claiming to know the exact countdown to the last star. We're saying that based on everything we observe, based on the best models we have, the number is approximately 1 trillion. It could be 700 billion, it could be 1.3 trillion, but it's in that range. And that level of precision across 2.5 million light-years of space is actually remarkable. To put 1 trillion in perspective, imagine counting. If you started now and counted one number every second without stopping to eat, sleep, or rest, it would take you about 31,700 years to reach 1 trillion. That's longer than all of recorded human history. It's longer than we've been farming, building cities, writing stories. You'd have to count through the rise and fall of every civilization we know, and you still wouldn't finish. Or think of it this way. If every star in Andromeda were a grain of sand, You'd need about 20 large dump trucks to hold them all. If every star were a drop of water, you'd fill more than 30 Olympic-sized swimming pools. If every star were a second, a trillion seconds would span almost 32,000 years. These comparisons don't make the number smaller, but they give it shape a form we can almost touch. Research shows that Andromeda contains roughly 2 to 3 times as many stars as the Milky Way. Our galaxy holds somewhere between 200 and 400 billion stars, depending on which estimate you trust. Andromeda is the larger sibling, the more massive neighbor. When you look up at that faint smudge in the night sky, you're seeing a galaxy that dwarfs our own. Why does Andromeda have more stars? Part of the answer lies in its history. Galaxies grow by consuming smaller galaxies, by pulling in gas and dust from their surroundings, by merging with neighbors over billions of years. Andromeda has been active. It's absorbed numerous smaller galaxies throughout its lifetime, each merger adding mass, adding stars, adding complexity. The streams of stars we see in its halo are evidence of this faint remnants of galaxies that no longer exist as separate entities. They're stars now part of Andromeda's vast population. The Milky Way has its own history of mergers, but Andromeda seems to have been more aggressive, more successful at gathering material. It's a reminder that galaxies aren't static. They're dynamic, evolving, shaped by their interactions with the cosmos around them. Comparing Andromeda to other galaxies puts the number in even broader context. Some galaxies are much smaller, dwarf galaxies containing only a few billion stars, sometimes less. Others are much larger, the Triangulum Galaxy. Another member of our local group contains perhaps 40 billion stars. The Sombrero Galaxy has around 100 billion. Giant elliptical galaxies like M87 can contain over 1 trillion stars, rivaling or exceeding Andromeda. So, Andromeda isn't the largest galaxy in the universe, not even close, but it's one of the largest in our local neighborhood, and it's the largest we can study in such detail. Its trillion stars make it a benchmark, a reference point, for understanding what a large spiral galaxy looks like, how it's structured, how its stellar population is distributed. One common mistake people make is assuming all galaxies contain similar numbers of stars. They don't. Galaxy size and mass vary enormously. The smallest dwarf galaxies might have only 1 million stars. The largest galaxies can have tens of trillions. The universe doesn't standardize. It creates diversity, a spectrum of possibilities, each galaxy a unique outcome of gravitational collapse, star formation, and cosmic evolution. Here's another way to think about 1 trillion stars. If you wanted to visit each star for just 1 second, no travel time between them, just 1 second of observation per star, it would take you 31,700 years. If you spent 1 minute at each star, it would take you 1.9 million years. If you spent 1 hour, it would be 114 million years. Even at the speed of light, traveling from star to star would take lifetimes beyond comprehension. The scale is almost cruelly vast. And yet, from Earth, from 2.5 million light years away, all those stars compress into a faint smudge. All that light, all that mass, all that complexity reduced to something you can barely see without a telescope. It's humbling. It's a reminder of how perspective changes everything, how distance transforms the grand into the subtle, the overwhelming into the gentle. Scientists suggest that if you could see Andromeda's full extent, not just the bright central core, but the entire disk and halo, it would span an area in the sky about 6 times the width of the full moon. But most of that area is too dim to see without long exposure photography. Our eyes catch only the brightest center, a hint of the whole. The rest exists in visible waiting. The number 1 trillion also carries implications for life. If even a tiny fraction of those stars host planets, and if an even smaller fraction of those planets are in the habitable zone, capable of supporting liquid water, the number of potentially life-bearing worlds in Andromeda is staggering. Suppose 1 in 100 stars has a rocky planet in the right orbit. That's 10 billion planets. Suppose 1 in 1,000 of those develops life. That's 10 million worlds with life. Suppose 1 in 1 million develops intelligent life. That's still 10 civilizations. These numbers are pure speculation, of course. We have no idea how common life is, let alone intelligent life. But the sheer size of the pool, the trillion stars providing a trillion opportunities, suggests that Andromeda might not be a sterile place. Somewhere in that vast spiral on some planet orbiting some ordinary star, something might be looking up at its own sky, wondering if it's alone. And here's a strange thought. If intelligent life exists in Andromeda, and if they have telescopes, they can see the Milky Way. To them, we're the distant neighbor, the faint spiral hanging in their night sky. They might be asking the same questions we are. How many stars does it have? Could life exist there? Are we alone? The distance between us and them, if they exist, is so vast that communication would be nearly impossible. A radio signal traveling at the speed of light would take 2.5 million years to cross the gap. By the time our message arrived, our civilization might be gone. By the time their reply returned, 5 million years would have passed. It's a silence enforced by physics, by the structure of space-time itself. But there's a beauty in that silence, too. It means that if life exists in Andromeda, it's living its own story, independent of ours, shaped by its own history, its own struggles, its own triumphs. We're not neighbors who can visit. We're distant witnesses sharing the same universe but separated by a gulf too wide to bridge. Have you ever felt small standing under the stars? Have you ever looked up and felt the weight of all that distance, all that time, all that light? The feeling isn't diminishment, it's connection. You're made of stardust. The atoms in your body were forged in stars that died long before the sun was born. You're part of this. The trillion stars in Andromeda are distant, yes, but they're also kin-fellow travelers in the cosmic dance. The uncertainty in the count, that range from 700 billion to 1.3 trillion, comes from several sources. One is the difficulty of measuring the faint stars, the red dwarfs that dominate the population, but contribute little light. Another is the challenge of mapping the halo, the outermost regions where stars are sparse and hard to detect. A third is the question of what counts as part of Andromeda. Some stars in the outer halo might have been captured from other galaxies. Are they Andromedan stars or interlopers? These aren't just technical quibbles. They reflect the messy reality of galaxies. Galaxies don't have sharp edges. They fade gradually into the intergalactic medium. Defining where one galaxy ends and another begins is surprisingly difficult. So, the count depends partly on where you draw the boundary, how you define membership. But regardless of those details, the order of magnitude is clear. Andromeda contains about 1 trillion stars. That's the scale we're dealing with. That's the reality we're trying to comprehend. 1 trillion stars. It's a number that asks us to expand our thinking, to embrace vastness, to accept that the universe operates on scales so large they defy intuition. It's a number that humbles and inspires in equal measure. And it's a number that will continue to be refined as our tools improve, as our methods become more sophisticated, as we learn to see fainter and farther into the cosmic dark. Every refinement brings us closer to the truth, even if we never reach it exactly. And maybe that's okay. Maybe the pursuit matters more than the precision. Maybe the act of counting the effort to understand, the willingness to sit with numbers so vast they break our mental models, maybe that's where the real value lies. In Andromeda, 1 trillion stars burn. Some are young hot blue. Some are old cool red. Some are dying, swelling into giants, shedding their outer layers into space. Some are being born, condensing from clouds of gas, igniting for the first time. It's a living system, constantly changing, constantly evolving, 1 trillion stories, unfolding across hundreds of thousands of light years. And we, from our small planet orbiting our average star in our moderately sized galaxy, we've managed to count them. Not perfectly, not exactly, but Well enough to know the scale, to understand the magnitude, to hold that number in our minds and feel its weight. That's an achievement. That's a testament to human curiosity, to our refusal to accept mystery as the final answer to our insistence on looking, measuring, calculating, understanding. But the story doesn't end with the number. Tools are improving. Technology is advancing. And the way we count stars, the way we study galaxies, is about to change in ways that would have seemed impossible just a generation ago. The future of counting the next frontier is already unfolding. What if in 20 years we could name every star in Andromeda? What if we could map not just the bright ones, the obvious ones, but every red dwarf, every dying giant, every newborn sun hidden in clouds of dust? What if we could watch them move, track their orbits, measure their chemistry, build a complete census of an entire galaxy from 2.5 million light years away? It sounds like science fiction, but it's becoming science fact. The tools we're building, the technologies we're deploying, are about to transform how we count stars, how we understand galaxies, how we perceive the universe itself. The future isn't just brighter telescopes, it's smarter telescopes. It's artificial intelligence sifting through oceans of data, finding patterns humans would miss. It's spacecraft positioned beyond Earth's atmosphere, seeing wavelengths our eyes can't detect. It's collaboration across continents, across disciplines, across generations. The next frontier in counting stars isn't just about technology. It's about imagination, patience, and the willingness to ask better questions. We've come so far already. From Al-Sufi's naked eye observation to Hubble's Cepheid variables to modern estimates of 1 trillion stars. But the story isn't over. It's accelerating. And the next chapter promises to be extraordinary. If you're curious about where science is headed, about the tools that will reshape our understanding in the years to come, perhaps you'd like to stay for this part of the journey. A gentle, like a quiet subscription, and that small bell keep you connected to these explorations, these glimpses into what we're learning and what we're about to discover. Now, let's look toward the future. One of the most transformative tools in modern astronomy is the James Webb Space Telescope, often called JWST, or simply Webb. Launched in December 2021, Webb is the most powerful space telescope ever built. It observes primarily in infrared, the wavelength where cool stars, dust-shrouded regions, and distant galaxies shine most brightly. Where Hubble gave us visible light, crisp and familiar, Webb gives us infrared, revealing what's hidden, what's cold, what's far. For counting stars in Andromeda, Webb changes everything. It can see red dwarfs that Hubble couldn't resolve. It can peer through dust clouds that obscure star-forming regions. It can detect individual stars in the outer halo, where they're sparse and faint. With Webb, astronomers can refine their population estimates, filling in gaps, correcting assumptions, bringing the count closer to reality. Scientists suggest that within the next decade, Webb will help us create detailed maps of Andromeda's stellar populations, region by region, identifying not just how many stars exist, but what types they are, how old they are, what they're made of. This level of detail was unimaginable a generation ago. Now it's within reach. Another groundbreaking project is the European Space Agency's Gaia mission. Gaia is mapping the Milky Way with unprecedented precision, measuring the positions, distances, and motions of over 1 billion stars in our own galaxy. It's creating a three-dimensional map, a census so detailed that we're learning things about the Milky Way's structure we never knew. Stars we thought were part of one spiral arm turn out to belong to another. Streams of stars reveal ancient mergers. The data is revolutionary. But Gaia's focus is the Milky Way. It's too far inside our galaxy to map Andromeda the same way. However, the techniques Gaia pioneered, the methods it developed for analyzing vast data sets, those can be adapted. Future missions, perhaps stationed outside our galaxy or using different approaches, might apply Gaia-like precision to external galaxies. Imagine a catalog of not just a billion stars, but a trillion each one, measured each one, tracked. It sounds impossible. And maybe it is at least for now. But science has a way of making the impossible routine. What once required years of painstaking observation now happens automatically. What once demanded rooms full of human computers now runs on algorithms in seconds. The trend is clear. We're getting better at this, faster, at this, more ambitious. Artificial intelligence and machine learning are playing an increasingly important role. Telescopes generate enormous amounts of data. A single night of observation can produce terabytes of images, spectra measurements. No human could analyze it all. But AI can. Machine learning algorithms can be trained to recognize stars, classify them by type, identify variables, detect anomalies. They work tirelessly without bias, without fatigue. Research shows that AI can classify millions of stars in the time it would take a human astronomer to classify hundreds. It's not replacing human insight, it's amplifying it. Astronomers train the algorithms, check their work, refine their parameters. But the heavy lifting, the repetitive sorting, and measuring that's done by machines. This frees astronomers to focus on interpretation, on asking why and how, on building theories that explain what the data reveals. In the context of Andromeda, AI could analyze images of the galaxy, identify every visible star estimate, the brightness and color of each, and feed that information into population models. It could do in hours what would take human teams years. And as the algorithms improve as they learn from more data, their accuracy will increase. We're approaching a time when the bottleneck isn't data collection, but data interpretation, when the challenge isn't seeing, but understanding. There's also the possibility of new types of observatories. Ground-based telescopes are getting larger. The extremely large telescope currently under construction in Chile will have a primary mirror 39 meters across, dwarfing anything that exists today. With adaptive optics to correct for atmospheric distortion, it will see almost as clearly as a space telescope, but with far more light-gathering power. Observatories like this will resolve individual stars in Andromeda's outer regions, measure their motions, track their evolution. And then there are space-based interferometers, arrays of telescopes working together to simulate a much larger aperture. By combining the light from multiple instruments, astronomers can achieve resolutions impossible with a single mirror. Proposals exist for missions that would place telescopes in formation, separated by thousands of kilometers, working in concert to map distant galaxies with exquisite detail. These missions are expensive, technically challenging, but not beyond our capability. They're waiting for funding, for political will, for the moment when humanity decides the investment is worth it. One particularly exciting concept is the idea of a galactic census. Instead of estimating stellar populations from integrated light and models, why not count the stars directly? Use automated surveys to image every region of a galaxy, identify every visible star, catalog them individually. For Andromeda, this would mean millions of images, billions of data points, a years-long campaign of observation and analysis. But the result would be a true census, a complete inventory, the most accurate count we've ever had. Scientists believe this is feasible within the next 20 to 30 years. Not easy, but possible. The technology exists or is being developed. The computational resources are growing. The will to do it, the recognition that such a project would advance our understanding of galaxy formation, stellar evolution, and cosmic history that's building too. But here's a lesson from history. Every time we improve our tools, we discover we were wrong about something. When Hubble first looked at Andromeda with a 100-inch telescope, he didn't just confirm it was a galaxy. He found it was farther away than anyone expected. When infrared telescopes first studied it, they didn't just see cool stars. They found complex dust structures, hidden star formation surprises. The same will happen with future observations. We'll refine the count, yes. We'll get closer to the true number. but we'll also discover things we didn't anticipate. Maybe there are more stars than we think hiding in regions we haven't observed carefully. Maybe there are fewer, and our models overestimated certain populations. Maybe the structure is more complex, the history messier, the reality stranger than our neat theories suggest. That's the beauty of science. It's not about confirming what we already believe. It's about being willing to be surprised, to adapt, to say, I was wrong, and move forward with better understanding. The number 1 trillion is our best estimate now. In 10 years, it might be 1.2 trillion, or 900 billion. And that's not failure, that's progress. Another frontier involves studying individual stars in Andromeda, not just counting them. With Webb and future telescopes, astronomers can take spectra of individual bright stars, measuring their composition, their temperature, their stage of life. They can identify Cepheid variables, red giants, supergiants, each one a data point in the story of the galaxy's evolution. By studying the oldest stars, the metal-poor relics from Andromeda's youth, astronomers can learn about conditions in the early universe. By studying the youngest stars, the hot blue giants in star-forming regions, they can understand what's happening now. Each star is a chapter. Together, they tell the full story. There's also the potential for citizen science. Projects like Galaxy Zoo have shown that ordinary people with no formal training can contribute to astronomical research. By examining images and classifying galaxies, volunteers have discovered rare objects, found anomalies, helped scientists sort through data that would otherwise sit unanalyzed. Future projects might ask people to help identify stars in Andromeda, mark variables, flag unusual spectra. It's democratic, it's inclusive, and it works. Have you ever wanted to contribute to science, to be part of something larger than yourself? The opportunity is growing. Astronomy is becoming more accessible, more collaborative. The data is increasingly public. The tools are increasingly user-friendly. The barriers are falling slowly but surely. One challenge that remains is funding. These missions, these telescopes, these computational projects, they're expensive. They require sustained investment over decades. Governments and agencies must prioritize them, recognizing that the return isn't immediate profit, but long-term knowledge, the kind of understanding that enriches humanity, even if it doesn't fill coffers. Historically, astronomy has faced this challenge before. Every major telescope, every significant mission required advocates, champions who believed the cost was worth it. Sometimes they succeeded, sometimes they didn't. The Hubble Space Telescope almost didn't happen. Budget cuts nearly killed it. But advocates persisted, and now it's one of the most productive scientific instruments ever built. The same perseverance will be needed for future projects. There's also the question of what we'll do with all this data once we have it. A complete census of Andromeda's stars isn't just a list. It's a foundation for countless follow-up studies. Which stars have planets, which are binaries, which are variables, which are dying, and which are being born. The census enables investigations that would be impossible without it. Scientists suggest that such a census could also serve as a baseline for detecting change. Galaxies evolve slowly, but they do evolve. Stars are born, stars die, supernovae explode. Over time, the population shifts. If we have a detailed snapshot from 2030 and another from 2060, we can measure that change directly. We can watch a galaxy evolve, not in simulations, but in reality. The future of counting stars isn't just about better numbers. It's about deeper understanding. It's about moving from how many to which ones and why. It's about building a relationship with Andromeda, learning its quirks, its history, its personality. Galaxies aren't just objects. They're systems, communities of stars and gas and dust, each one unique. In a sense, we're learning to see Andromeda the way we see Earth, not just as a sphere of rock and water, but as a living, changing, complex system with weather ecosystems history. We're learning to see Andromeda as a place, not just a thing, A place we can't visit, perhaps, but a place we can know deeply and intimately. And as our tools improve, as our methods refine, as our patience and curiosity drive us forward, the knowledge grows. The count becomes more accurate. The uncertainties shrink. The picture sharpens. But the wonder doesn't diminish. If anything, it deepens. Because every answer opens new questions. Every discovery reveals new mysteries. The universe doesn't run out of secrets. 1 trillion stars. For now, that's the number. But it's not the end. It's a milestone, a marker on a journey that started with Al-Sufi's naked eye and continues into a future where artificial intelligence-based telescopes and human ingenuity combine to push the boundaries of what we can know. The next generation of astronomers will count stars we can't yet see. They'll answer questions we haven't yet asked. They'll stand on our shoulders the way we stand on the shoulders of those who came before. And maybe they'll look back at our estimate of 1 trillion and smile the way we smile at the astronomers who thought Andromeda was a cloud or a nebula or part of the Milky Way. They'll see how far we came with what we had, and they'll push farther still. But even with all these tools, all this future promise, there's something we haven't yet touched. Something that brings all these numbers, all these methods, all these stars back to a single simple feeling. The feeling of looking up. The feeling of knowing. The feeling of being small and vast at once. And that's where we drift now toward the quiet conclusion of this journey. We've traveled far tonight. From a faint smudge in the sky to 1 trillion points of light. From ancient observers with nothing but their eyes to modern scientists with telescopes that see across millions of light years. From mystery to measurement, from wonder to knowledge. And now, as we near the end of this quiet journey, it's time to step back, to let the numbers fade, to remember what this was really about. How many stars are there in the Andromeda Galaxy? 1 trillion, give or take. But that number, as vast as it is, was never the true answer. The true answer is simpler, stranger, more beautiful. The true answer is enough. Enough to fill the darkness. Enough to make us pause. Enough to remind us that the universe is larger than our questions, deeper than our measurements, richer than any count could capture. Tonight we asked a question about stars, but what we found was a story about us. About how we look at the sky and refuse to accept ignorance, about how we build tools to extend our senses mathematics, to sharpen our thinking collaboration to amplify our reach, about how we take something unreachable and make it knowable not by touching it, but by understanding it. Think about the journey we've taken. We started with Abd al-Rahman al-Sufi in the year 964, looking up at the night sky over Isfahan, seeing a small cloud and writing it down. He didn't know what it was. He had no telescope, no spectrograph, no computer, just eyes, patience, and the belief that what he saw mattered enough to record. Then we moved through centuries, through Galileo, who revolutionized astronomy but never noticed Andromeda, through Charles Messier, who cataloged it as an annoyance, something to avoid while hunting comets. Through the Great Debate of 1920, when brilliant minds stood on opposite sides of a fundamental question about the universe's scale. Through Edwin Hubble, who found Cepheid variables and proved that Andromeda was a galaxy, separate and distant, expanding our cosmos overnight. We explored the architecture of galaxies, the bulge dense with ancient stars, the disk spinning slowly adorned with spiral arms where new stars ignite, the halo vast and ghostly filled with remnants of smaller galaxies consumed long ago. We learned that structure matters, that you can't count what you don't understand, that every region tells a different part of the story. We delved into the mathematics of starlight. How do you count what you can't see? You measure brightness, analyze color, calculate mass, infer populations. You trust in physics and patterns observed nearby and assumed universal. You build models, test them, refine them, accept uncertainty as part of the process. The number 1 trillion isn't a fact carved in stone. It's an estimate, a best guess built on solid foundations, but always open to revision. We discovered the hidden majority, the red dwarfs, small, cool, dim, outnumbering all other stars combined. They make up perhaps 70 or 80% of Andromeda's stellar population, yet they contribute barely a fraction of its light. They're the quiet ones, the patient ones, the stars that will outlive everything else. They remind us that what matters most isn't always what shines brightest. We confronted the number itself. 1 trillion, a number so large it defies comprehension, so vast, we need metaphors to bring it down to human scale. 31,000 years to count at 1 per second. 20 dump trucks of sand, 30 Olympic pools of water. And yet from Earth, all that light compresses into a faint smudge, something you might miss if you're not looking carefully. We look toward the future. The James Webb Space Telescope peering into infrared, revealing what was hidden. The Gaia mission mapping the Milky Way with exquisite precision, pioneering techniques that might someday map other galaxies. Artificial intelligence sifting through data oceans, finding patterns faster than any human could. The promise of a true galactic census, a complete inventory of stars, achievable within our lifetimes if we commit to it. And now, here we are, at the end of the count, but not the end of the story, because the story of Andromeda is also the story of the Milky Way. It's the story of every galaxy, every star, every world. It's the story of matter organizing itself, of gravity pulling gas into clumps that ignite into fusion of light, spreading across the void, carrying information, carrying energy, carrying the possibility of connection. Research shows that in about 4.5 billion years, Andromeda and the Milky Way will collide. It won't be violent. Galaxies don't crash like cars. The stars are too far apart, the space between them, too vast. When the galaxies pass through each other, almost no stars will actually touch, but gravity will pull them together, reshape them, merge them into something new. Astronomers have already named this future galaxy Milkomeda, or sometimes Milkdromeda. A blend of both names, a union of both histories. The trillion stars of Andromeda will mingle with the hundreds of billions of stars in the Milky Way. New structures will form. New spiral arms, perhaps. Or maybe an elliptical galaxy, smooth and featureless, the spiral structure erased by the chaos of merger. By then, our sun will be older, cooler, possibly nearing the end of its life. Earth might not exist as a habitable world. Humanity, if it still exists, might have spread to other stars, other galaxies, or vanished entirely. But the stars themselves, many of them will endure. They'll dance together in a new configuration, orbiting a new center part of a new cosmic structure. It's strange to think about, isn't it, that the distant neighbor we've been studying, counting, measuring from afar, is also coming closer. That distance isn't permanent. That even galaxies in their slow, patient way are reaching for each other. It's like learning that a stranger you've been watching from across a room is actually walking toward you, slowly, inevitably, and one day you'll meet. But that meeting is billions of years away. For now, Andromeda remains separate, distant. A trillion stars spinning through the void, each one a sun, each one potentially surrounded by worlds, by moons, by possibilities we can only imagine. And what about us? What about the people who counted those stars, who asked the question, who refused to accept "we don't know" as a final answer? We're here, on this small planet, orbiting an average star, in an ordinary location within an average galaxy, and yet we looked up, we wondered, we measured, we understood. That's not ordinary, that's extraordinary. That's what makes us human, not our size, which is negligible, not our strength, which is laughable on cosmic scales, not our lifespan, which is a blink, but our curiosity, our persistence, our ability to look at something vast and distant and incomprehensible and say, "I want to know, I will find a way." Have you ever felt that pull, that desire to understand something beyond yourself, beyond your immediate needs, beyond your lifespan? That's what drove Al-Sufi. That's what drove Hubble. That's what drives astronomers today, staying up through cold nights analyzing data until their eyes blur, writing papers that few will read all because they need to know. All because the question won't let them rest. We are made of stardust. That's not metaphor, that's chemistry. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was forged in stars that died before the sun was born. Those stars exploded, scattering their material into space, and that material eventually coalesced into new stars, new planets, new life. You are literally made of star stuff, and so is everything around you. The screen you're looking at, the air you're breathing, the planet beneath your feet, all of it star stuff. Recycled, reformed, given new shape, new purpose, new meaning. In Andromeda, the same process is happening. Stars are dying, enriching the galaxy with heavy elements. New stars are forming from that enriched gas. Planets are condensing. And maybe on some of those planets, something is looking up at its sky, wondering if it's alone, asking questions it doesn't yet have the tools to answer. If they exist, those distant wanderers, they can't see us. Not as individuals, not even as a civilization. From Andromeda, Earth is invisible, a pale blue dot lost in the glare of our sun. But they can see our galaxy. The Milky Way is visible from Andromeda, a faint smudge in their sky, just as Andromeda is a faint smudge in ours. Maybe they're asking the same question. How many stars are there in that distant spiral? Maybe they've built telescopes, taken measurements, made estimates. Maybe they've arrived at their own number, their own understanding. Maybe they've wondered as we have if they're alone. The silence between us isn't emptiness, it's patience. It's the universe giving each of us space to grow, to learn to become what we're meant to be without interference. The 2.5 million light years that separate us from Andromeda is a gift, a buffer, a guarantee that whatever happens, there happens independently, that their story is theirs and ours is ours. But it's also a reminder of connection, because the same laws of physics operate there. The same forces shape their stars, their galaxies, their worlds. Gravity works the same, fusion works the same, light travels at the same speed. We are separate, yes, but we're also part of the same universe, governed by the same rules, built from the same materials. Knowledge in the end isn't about conquering the unknown. It's about relationship. It's about learning to see the universe not as a collection of objects, but as a system, a web of connections where everything influences everything else. Andromeda influences the Milky Way through gravity. The Milky Way influences Andromeda. Together, they're part of a larger structure, the local group, which is part of a cluster, which is part of a supercluster, which is part of the cosmic web that spans the observable universe. We're not separate from this. We're part of it. Every time you look up at the night sky, you're participating in it. Your eyes are collecting photons that left Andromeda millions of years ago. Those photons traveled through space, through time to reach you. And in that moment of seeing, you're connected, not physically, but through light, through information, through the simple act of witnessing. Tonight we counted stars, but what we really did was honor them. We acknowledged their existence, their significance, their beauty. We said, you matter, even though you're far away, even though we'll never touch you, even though you might not know we exist, you matter to us. We see you. We count you. We remember you. And maybe that's enough. Maybe the act of counting, the effort to understand, the willingness to sit with vastness and not turn away. Maybe that's the real achievement, not the number itself, but the journey to find it. Not the answer, but the question. 1 trillion stars, each one a furnace of fusion, each one converting mass into energy, radiating light across the void. Each one obeying the same laws, following the same physics, burning with the same patient fire. And all of them together, a galaxy. A community of stars bound by gravity, shaped by history, evolving slowly across billions of years. We've walked through neurons and dreams, through light and silence. We've explored distances too vast to travel, numbers too large to grasp, stories too old to witness. Maybe knowledge was never meant to be kept, only felt for a moment. Maybe understanding isn't about certainty, but about connection, about seeing ourselves in the stars and the stars in ourselves. As this night draws to a close, as your eyes grow heavy and your thoughts drift towards sleep, carry this with you. You are part of something vast. You are made of stars. You are connected to galaxies, to light that has traveled for millions of years, to questions that span centuries, to a universe that is both incomprehensibly large and intimately close. Andromeda is out there, a trillion stars spinning softly through the darkness. You can't see most of them. You can't reach any of them, but you know they're there, and in knowing you're changed, the universe becomes richer. Your place in it becomes clearer. The night becomes less empty and more full. Thank you for staying with me through this gentle journey. Thank you for your curiosity, your patience, your willingness to drift through cosmic distances and mathematical vastness without rushing, without demanding quick answers. These quiet explorations matter. They remind us that learning doesn't have to be loud, that wonder can be whispered, that knowledge can be a lullaby. If you found comfort here, if this journey brought you peace or sparked your curiosity, there are more stories waiting, more quiet nights, more questions asked softly, more science told like poetry, where precision meets wonder and facts become dreams. We'll explore them together, one gentle night at a time. Until then, sleep well, dream gently, and when you look up at the night sky, remember somewhere in that darkness, Andromeda glows. A trillion suns burning patiently, waiting, shining, holding the universe together with quiet gravity and ancient light. Good night,